So in calculus today, we picked up lesson 2.1 again, and we just talked about this example here that we kind of left off with on Thursday of last week. And so rather than take the time to actually cube x plus delta x, we just decided we know how to cube something, we just decided to go with, here's the answer. You guys can work on this later on your own time. So I supplied the answer to that problem and we went on. In second hour, I did not do this problem, but in hindsight, I wish I would have. So in sixth hour, we did go through this problem right here, and we talked about how to find the derivative. This one was especially good because we had to get a common denominator here and here and work it out algebraically, and we found our derivative to be negative 2 over t squared. Again, with this one, t was our variable, not x, so everything was in terms of t. And then we went through this example here where we found the slope first, and basically that gave us this formula for slope. So when we were all done with that, we got negative 2x. We plugged in 2 for our x right here, and we got a slope of negative 4. And then we wrote the equation of our line. Then we tackled number 5, and I will attach a picture of the work for that one on Canvas here in a little bit. So look for that coming up soon. Then we started talking about vertical tangent lines, and so a vertical tangent line happens when you try to find the tangent line at C, and that tangent line is vertical. And we have some different ways to say differentiability implies continuity. So the first one is a very basic if-then statement. So if a function's differentiable at C, then we could say it's continuous. And it's also true to say if a function is not continuous at C, then it's also not differentiable. However, the inverse of the above statement is not true. Continuity does not imply differentiability, so pay attention here. Just because you have a function that is continuous doesn't mean you can differentiate all the way through the curve. For example, here's the absolute value of x minus 2. I can find the derivative on the left side, it's negative 1. And I can find the derivative on the right side, it's 1. And those are just the slopes of those two lines. But at 2, I cannot find the derivative. And I'll show you why that is here in a little bit when we look at the alternative form of a derivative. So even though this guy is continuous all the way through negative infinity to infinity, it is not going to be differentiable at 2. All right, this is called the alternative form of the derivative. It's another way to find a derivative. And it says f prime of c is the limit as x approaches c of f of x minus f of c over x minus c. And so what's happening here is this is going to just give you the slope at a particular point. It's no different than y minus y over x minus x. And so this is very handy to see if a derivative exists at a particular point. And when we come up with the fact that it does not exist at that particular x value, then more than likely we have a vertical tangent there. And so we started off with examples of this, and the first one we got through today, and these are just the notes from sixth hour. We didn't get as far. We just looked at the sharp turn problem. So with the sharp turn, you're going to want to go ahead and find this right here. And so if I decide to go with this formula, I would have f prime at 2, which is where the sharp turn occurs, is the limit as x approaches 2 of our function x minus 2 minus 0 over x minus 2. If I try to directly plug 2 into the numerator and denominator, I get 0 over 0. When that happens, I have to go and split my function into the left side and the right side. And so that's what I'm showing here in orange. I took the derivative as we approach 2 from the left and from the right, or I took the limit as we approach 2 from both ways. Your class had trouble reading those, so we came over here and we created the graph to go with that. So the graph here explains how we got -1 and 1. All right, because these are two different values, the limit at 2 does not exist, and so that implies then that your derivative here does not exist. And that's basically where we stopped in hour 6. So I will pick up the rest of those notes with hour 6 tomorrow, and in hour 2 we will go back over some of these topics again. Hope you guys are doing well. Hope to see you tomorrow.